Welcome back to ECE 442-542. This is the next to the last time that we meet before the final exam. The final exam is a week from Thursday. It's the last day of finals. But before that, we have a few things that are due. If you're in 542, your project is due. There is an extra credit homework assignment that's due on reading day at 11:59. The teacher course evaluations are due on the last day of class, and stay tuned. I may still give you extra credit for that. The percentage of students that have so far completed that is a little low. So I would like to get that up, and it means more if I have a higher percentage or I have a higher fraction of students completing that in terms of other faculty believing the results. So it does influence my interpretation or how I want to continue the class in terms of the material, but it also is used to assess how well I'm doing as an instructor in this class. And so for that reason, it is important to me and to others. I think what I will probably do is post, this will be lecture 8.2, today's lecture. I think I will go ahead and post something from a previous semester 3 years ago and call that lecture 8.3, which will be an example of how you can do this, and it will be dealing with the mass spring damper system that if you've been in 441 or 541, we used that before, but now we'll use that information to inform the model that we're using in that MATLAB example. If you've pulled up your head from the senior project at all and looked at D2L, there's actually another unit that's addressing the final exam, and it has a review lecture and notes, and I decided to go ahead and post that from a previous semester. It's fairly similar to this semester, and that gives you more time to look at that or to think about the final instead of maybe having that during finals week. I think it will be better to just go ahead and allow you to have access to that now, and that's presently available to you. And as I said, the final exam is Thursday, the 11th of May from 1 to 3, and it will be in this room. Notation we've already talked about, continuous time state space and discrete time state space. Today we'll start by reviewing the regulator design, or when we simply apply an input that is proportional or scaled version of the full state vector. And in that case, this K is a matrix. It's not necessarily a scalar. Now, if you had one input and one state variable, a first order system, K, that matrix would be a 1-by-1 matrix. It would be a scalar. So you can have K being short and wide, but depending on how many state variables you have, the width of that K matrix can start to collapse. And if your state vector, if you just have one state variable, then you in fact do have a scalar full state feedback gain matrix K, which is a matrix that's 1-by-1. But we're going to call that a regulator design when we don't have a formal way of injecting a reference input to track. We'll then talk about when is it actually possible to perform full state feedback or to make this assignment of closed loop poles anywhere we want in the z-plane, and obviously you probably want those to be inside the unit circle, and you know that you have the target or the circle, you have the heart, and you have the wedges to inform where you place your dominant poles. Maybe you place 2 poles of a 10-pole system at this dominant location informed by the circles, the hearts, and the wedge, and then maybe you put all the others at the origin. If you had 10 poles, you would do 2. Those would dominate. Those would be complex conjugate at those circle, hearts, and wedge locations. and then the other 8 would be at the origin. That's one way of sort of thinking about where do I put all of these poles in a full state feedback design. That is possible if your system is controllable. And we'll talk about building or constructing the controllability matrix, and if that is full rank, and in our case, if we have a single input, then it will just be, can we find a non-zero determinant for the controllability matrix, then we'll be good. So the in-class speakers I've decided to not do anymore because it actually was making the audio terrible. So I've disconnected one of the paths, and so I apologize if I'm screaming to the people that are listening to this, but I think the audio is a better quality if I don't try to use the room speaker system. And maybe the next time I come into this class, it's not going to be Wednesday, but the next time I teach, maybe I'll go ahead and pipe it out to the room speakers. I'll have some other thing worked out. But right now it's not working the way I would like it to work. So thanks. What I'm looking for now, so if you see me looking, I'm looking at my receiver to make sure I see 2 lights, that the antenna is actually receiving the signal. Typically, I've been informed by the speakers in the room. Now I don't have that feedback mechanism. Now I have to do a visual check every once in a while to see if I am being recorded. We now have done a regulator design. We've checked controllability. The next step is to go ahead and say, how can we make a tracking system or have a reference input? How can we now drive this system where we want it to go? How can we make it follow some reference input? That's going to be then full state feedback with a reference input. And now we will have an additional signal in place in addition to the normal full state feedback. And this last point is lecture 8.3. Probably, I don't know that we will get there today. That's the mass spring damper system. And next time, I think what we will talk about is augmenting this full state feedback design to allow us to put in an integrator so that we can not have to be so concerned about exactly modeling or matching the true system's model or representation with our model of the system. Because if we are off, then this full state feedback with reference input could be introducing some errors, or we could have some tracking error, even though we set the DC gain to 1. But with an integrator introduced, we can integrate that error away or remove it. Here is our full state feedback review from the previous lecture. We have the system represented in state space form, and this vector x is n rows tall, 1 column wide, Nevada tall. The number of inputs u can be more than 1. It could have m such inputs. But typically in this class, we're going to focus or concentrate on M, Michigan, being 1. And the output Y is now seen through this mapping matrix H, our output matrix H, which takes a linear combination of the state variables, and how many of those outputs we have available or measure depends on how many rows we have in H. And right now, notation-wise, I'm saying we have Q of those. So we have N state variables, Nevada of those. We have M, Michigan inputs, and that now tells us how wide gamma is. Gamma is as tall as we have state variables, but it's as wide as we have inputs. H, our output matrix, is possibly tall, but typically in this class it's going to be short and wide. where short is maybe we just have one output and the width of h is consistent with the number of state variables we have. All of these matrices have to be compatible, meaning phi times x needs to produce a n by 1 vector. So phi has to be square, and it's n by n. What we are going through now is different from what we've been doing in the transform or transfer function-based controller approach. Now we're saying, let's assume that we can go in and measure every one of those state variables, components. So our state variables might be position, velocity, voltage, current, temperature, pressure. How many did I just label? 5 or 6? We may have 6 different state variables. We're saying then in this full state feedback design that we can go in and access each of those at the time instant L. We can now measure the position, the velocity, the voltage, the current, the temperature, and pressure. And we can scale each of those by some parameter that's included in the state feedback gain matrix K, where K is now K1, K2, K3, K4, etc. That now makes up our input U of L into this system, and all of that then allows us to build up the next, or the state vector, one time step in the future, x at time L plus 1. That's the picture, and the system, the plant that we're playing with, is really defined by what's highlighted. That's our system, and we are now going inside the system, not measuring the output. We're saying we can go inside the system and have access to those state variables, scale those, and make those our input U. And next time we'll talk about, next time being next lecture, how can we maybe get beyond that and maybe restrict ourselves to only having access to the output. How do we still use some of these strategies that we're talking about today as far as full state feedback? In our example that we talked about last time, we picked a 2x2, or we had a second order system, phi, and its system matrix was 2, 1, 0, 0. We can look at the open loop dynamics by finding the eigenvalues of that system matrix, phi. And the eigenvalues are just the determinant of Zi minus phi. The identity matrix needs to be compatible with the phi matrix, so it's 2x2 with 1s on the diagonal. And if we do that, we have the product of the diagonals minus the product of the off diagonals, and we end up with this characteristic polynomial of z times z minus 2. When we set that equal to 0, what values of z cause that characteristic polynomial to vanish? Those are our open loop eigenvalues. And the open loop eigenvalues now, in this particular case, are at the origin and at z equal to 2. And if they are at z equal to 2, what do we know about the stability? Now we know that we have an unstable system, because we're outside the unit circle, and we probably want to do something to adjust that system so that it now is stabilized. And the way that we're going to do that today is via full state feedback. And if we wanted to, we could actually find our transfer function of the system by looking at g of z, which is now h, the output matrix, times zi minus phi inverse times gamma. And with full state feedback, we have now U of L is equal to minus KX of L. And the reason we want to use full state feedback is so we can change the open loop dynamics from being something that we don't want. In this case, it's pretty clear that we don't want those open loop eigenvalues because we had one outside the unit circle. Now we have U of L is equal to minus KX of L. So if we use K to move the closed loop eigenvalues, I'm getting hints. Maybe I'm interpreting these hints wrong. But we can use K to move the open loop eigenvalues to more desirable locations, and those desirable locations are based on the circle, the heart, and the wedge. And the way that we will do that is we will find the characteristic polynomial with these unknown gain values in our full state feedback gain matrix. That's what I'm meaning by delta sub k of z, and we'll set that equal to our desired characteristic polynomial, delta sub d of z. The delta sub d of z is based on the dominant behavior that we want. Either we choose what that delta sub d of z is, or somebody gives us those dominant poles that we want to have, and then we need to calculate this characteristic polynomial in terms of these unknown or yet to be determined k values in our full state feedback gain matrix. In our example, we said let's just assume we want closed loop poles at 0.8 plus and minus j 0.2. And are those at least stable? Now you just have to find their magnitude. And this would be the real part squared, which is 0.64, plus the imaginary part squared, which is 0.2 squared. So now we have 0.64 plus 0.04, or 0.68. That's less than 1. So these are okay. And we want to now, with those desired pole locations, we want to create this delta sub d of z. And you don't have to do the next few steps. You can start further down the path than what I'm illustrating, but I want you to just see where this comes from once, and then you don't have to really do it again. But we want to now build this desired characteristic polynomial, and these values of a pole at 0.8 plus j 0.2 will cause this first factor to vanish. That will then set that delta sub d of z equal to 0. And a z value of 0.8 minus j 0.2 will cause the second one to vanish. So these are now roots of this desired characteristic polynomial. And if we now associate or collect these different pieces of this expression, let's now collect z minus 0.8. That's the real part. Right on cue, we have our stapler, and it's almost right at 550, so at least she's staying true to form. Somebody's paying her and she's getting paid, right? She's earning her pay. So now we have this product just written a little differently, and now you can do FOIL, or your favorite way of trying to multiply these two first-order polynomials, and I hope you can see that the cross terms cancel because one has minus j 0.2 and the other one has plus j 0.2. Or we now have minus the product of j.2 times j.2. And j squared is minus 1. That causes the negative sign to become positive, and this is actually maybe where you would start if you were doing this design on an exam. and somebody said, oh, I want my dominant poles to be at 0.8 plus and minus j 0.2, you might say, oh, I can build up my desired characteristic polynomial by just taking z minus 0.8, squaring that, and adding to that the imaginary part squared. And I hope then the previous 3 lines justify or help you understand where that comes from. Now that you know where that comes from, you don't have to continue to do that unless you want to convince yourself on the exam. But once you have this, now you have a second order polynomial that you can build. And what we want to do is, this is where we want to live inside the unit circle based on this characteristic polynomial, and this is going to be what we use to force these closed loop, or these full state feedback gain values, the K1 and K2 in this case, to try to match this polynomial with our characteristic polynomial that's a function of those adjustable parameters, K1 and K2. Or if we now apply full state feedback and create this characteristic polynomial as a function of the unknown k's, that's now this determinant of zi minus the closed loop system matrix. And the closed loop system matrix is phi minus gamma k. And I may at some point call that capital Phi sub c for the closed loop system matrix. But right now, that is going to contain these unknown state feedback coefficients, k sub 1 and k sub 2. These are the values that we're trying to find. And we can simply perform the algebra based on finding the determinant of zi minus phi sub c, where phi is 2100, gamma is 0.3. What's going to happen when we multiply gamma times k? You're going to get a 4-element matrix that's 2 by 2, right? Yeah, you should have said 3 by 3. Threes are not wild tonight, I hope. But we have a 2 by 2 matrix. It has to be compatible with phi, and it has to be compatible with zi. And the identity matrix needs to be 2 by 2. Putting in some more steps, then we see we have the zi as just z's on the diagonal, and the phi minus gamma k ends up giving us now a -2, a -1, and the k's only enter through the bottom row because gamma's first row is all 0. That annihilates anything that would be multiplied by it in this gamma matrix. Gamma k then only produces something in the second row of that product. Now we can use our knowledge of finding the determinant of a 2 by 2 matrix, which is just the product of the diagonals minus the product of the off diagonals, to produce the factor z minus 2 times z plus 3k sub 2 minus -1 times 3k sub 1. Multiplying that out, we now have z squared. We have a linear term that has a coefficient of -2 plus 3k sub 2, and our constant coefficient is -6k sub 2 plus 3k sub 1. What we are wanting to do is select k1 and k2 so that we force that characteristic polynomial that involves the k's to equal the desired pole locations. And if we had a fourth order system, then this would be a fourth order characteristic polynomial. We would have a k1 if we had a single input. We would have a k1, a k2, a k3, and a k4. and this delta sub d of z would be a fourth order. Maybe we would pick two of those roots to be dominant, and maybe the last two would be at the origin. So that wouldn't be that difficult to build. And then we now set all of those coefficients, or we compare coefficients in those two polynomials. And that's what we're doing when we connect or equate delta sub d of z with delta sub k of z. And in general, that will give you, in this case, two equations and two unknowns. We have two unknowns because we have the K1 and K2. If it was a 4x4, we would have four equations and four unknowns. On the final, if I give you a 10x10 phi matrix, then you have a 10th order characteristic polynomial, and now you have a 10 equations, 10 unknowns problem to solve. Again, just inverting a 10x10 matrix after you've already symbolically found the determinant of that 10x10 matrix. No big deal. That's the right answer. But in reality, you could let some software package do this for you. But you need to be able to do this for 2x2 matrices. In so doing, if we equate the coefficients that scale the constant, that scale the z to the first power, then we have minus 1.6 equaling minus 2 plus 3k sub 2. In general, there could be a k1 sprinkled in that, but in this case, it's just a function of k sub 2, so we can solve that by itself, and we immediately now have decoupled that two equations, two unknowns problem into sort of two first-order equations to solve. K sub 2 is now 0.1333, and we can use the constant coefficients in those two polynomials to find K sub 1. Since we already know what K sub 2 is, now K sub 1 ends up being about 1/2, or 0.4933. Once we've found K1 and K2, now you can build this full state feedback gain matrix. And one of the problems that I will see on the final exam is students will write this as a column and instead of as a row. They'll stack K1 on top of K2. When K1 needs to be compatible with U and X, where U is now equal to minus KX, if you have one input, then the product of K with X needs to give you a scalar. And if K is 1/2, multiplying a 2/1, that will give you a scalar 1/1. So one of the tips that you get for attending today's lecture is make sure you get the dimensions of K right. K needs to be, if you have a single input, it needs to be short and wide. Now let's continue with this example. We'll slow it down a little bit, and let's now apply this full state feedback gain matrix to our system and see if we're actually able to achieve the closed loop poles that we wanted. So applying full state feedback, we have x of L plus 1 is equal to our system matrix phi times x of L plus gamma, our input matrix, times U of L, but we're assuming full state feedback, so in this case it's minus K x of L. Or combining or factoring out the state vector from those two terms, we now have this open loop system matrix phi minus gamma K times x of L, so that this resulting matrix, which now everything is known. We know phi, we know gamma, and we know k. Phi sub c is just going to be a 2 by 2 matrix, 4 elements in that phi sub c matrix that are specified. Where this is now our closed loop system matrix, as opposed to the open loop system matrix, which was just phi. Now we've changed the dynamics of our system. It will now shake differently. Before, what would happen? If it was kicked, if phi was kicked in this example, what would have happened? If you would have initiated or excited those modes in the system, what would have happened with this phi that we started with? Where were our modes? Where were our eigenvalues? Where were our open loop poles? We had one at 0 and one at 2. So if that 2 mode gets excited in some way with a disturbance or some kind of offset, it's going to grow unbounded. Now what we want to do is have somebody walk up and kick this system, phi sub c, and it's well behaved. So we'll kick it again. And it's well behaved because it has poles at 0.8 plus and minus j 0.2. And those are inside the unit circle. Or doing that, we had phi, and since phi is upper triangular, the eigenvalues are immediately obvious. They're on the diagonal. One's at the origin and one's at 2. Our gamma matrix was 0, 3, and our K matrix had a K1 of 0.49 and a K sub 2 of 0.133. Doing the matrix algebra, we now would obtain phi sub c, and you can see that since we have a hard 0 in the upper row of gamma, the top row of phi sub c is not changed. That's still 2 and 1, but the bottom row does get modified from all 0. Now we have 3 times 0.4933 with a negative sign in the 2-1 entry, and in the 2-2 entry we have 3 times 0.133, which is actually now minus 0.4. And if somebody wants to know as a check, what are the dynamics now that we're kicking this system, what would you do? How would you determine the dynamics? If you were now, and maybe you had to answer that today during your judging, if you were in this ballroom dancing, no, if you were in the ballroom performing with your capstone project and somebody walked up and said, what are the dynamics of this system? And you said, the closed loop dynamics. How would you find the closed loop dynamics? If they know that this phi sub c is on your paper or on your poster, what does that correspond to? Those are our eigenvalues. We want to find the eigenvalues of this phi sub c matrix. And those would be your closed loop poles using full state feedback. So these, another way of talking about the dynamics, would say, oh, you want to know what my closed loop eigenvalues are equal to. And again, if we're taking the final exam, we need to be able to do this for at least a 2 by 2 matrix. This is now zi minus phi sub c's determinant, or it's now z times a 2 by 2 identity matrix minus the phi sub c, or that's now z minus 2 we have a -1, we have a 1.48, and we have a z plus 0.4. Or the diagonal terms multiplied together minus the product of the off diagonals. And now we have z squared. We have the linear terms are now -2 plus 0.4, or that will now be minus 1.6z. We have minus 0.8 plus 1.48. Or we take 1.48 and subtract 0.8. We now have 0.68, which that's exactly what we had for delta sub d of z, our desired characteristic polynomial for the second order. Or this now gives us values of z that satisfy that from our quadratic formula. If you wanted to use that, is now 0.8 plus and minus j 0.2. And that's now where we wanted. We wanted to achieve closed loop behavior governed by poles at point or eigenvalues at 0.8 plus and minus j 0.2, and we've now calculated k's and verified that those k's indeed give us those desired values for closed loop poles. What we want to do now is actually sort of step back and say, when is this always, or when will this be possible to do, to locate closed loop poles wherever we want in the z-plane? And that's what this concept of controllability is concerned with. We want to now ask the question, when is it possible for full state feedback to position the closed loop poles wherever we want in the complex z-plane, or arbitrarily? So we want to have a mechanism or a way, a procedure for checking before we even get started, before we start building this desired polynomial, before we start building this polynomial that's a function of all of these k's. Is it even possible to locate the closed loop poles? This would be your first step in this full state feedback process. We're just going at it now because I wanted you to sort of see the end result by doing it through an example. But now this would be your first step in a full state feedback design. You would basically be saying, is this system controllable? If it is, when is it possible for full state feedback to position the closed loop poles arbitrarily? The answer is when your system is controllable. And now what we want to do is present the way that you check whether a system is controllable or not. A system is in fact controllable if and only if the following matrix is full rank, where the matrix, let me try that again. Let me try to make a script. If I wouldn't slow down, it would be easier, but I stopped halfway through. But that's supposed to be a script C, and that's now made up of combinations of the input matrix gamma and the open loop system matrix phi. We start by simply putting in all of our input columns in the system, in the input matrix gamma. Next to that, we pack in the columns created by multiplying phi with gamma. Then we add another set of columns. This set of columns will only be one column if we add a single input for our system, where gamma is now one column wide. But the next columns that we pack in will be pre-multiplying phi gamma on the left with phi. And we just keep doing that. Now, the final exam is time limited, so we're not going to keep going with this. We go until we've multiplied n minus 1 of these phis together. And then we hit it with gamma. Actually, you would just create phi gamma, then hit that with phi to give you phi squared, hit that with phi to give you phi cubed gamma, etc. Up until phi of Nevada minus 1. So if we did have this 10th order system, little n Nevada is 10, so we would need phi to the 9th times gamma. We want this controllability matrix, this script C. If our system is to be controllable, we want this controllability matrix we want that to be full rank. By that, we mean that every row in this controllability matrix is linearly independent. That's what we mean by full rank. And if we simply have one input, gamma is Nevada by 1, or it's one column wide, this controllability matrix will actually be Nevada rows tall and 0 up to Nevada minus 1, or Nevada columns wide. It will be square. And if we have a square matrix and we want to know, does it have linearly independent rows? Well, if its determinant is non-zero, it has linearly independent rows, or it has linearly independent columns. It's the same check. Let me write that down, and because that's really the situation that we will be playing with mostly in this class. If little m is equal to 1, that's this single input case, or one input case, then our controllability matrix is square, and we need the determinant of that controllability matrix to be non-zero. It could be negative as long as it's not equal to 0. We need it to be non-zero for the system to be controllable. Let's go back to our example. Suppose we now have our system matrix phi, and this is the open loop system matrix. That's now 2, 1, 0, 0. Our input matrix was 0, 3. So in this case, we actually have one input. Little m is 1 and n is 2. The number of state variables is 2. So that our controllability matrix is gamma, phi gamma, phi squared gamma, phi cubed. No? Okay. I just was checking to see if everyone was paying attention. How many phis do we need? We just need n minus 1, so we need 2 minus 1. We can erase some of these. We simply need to do that multiplication once. We just need gamma, put that column in, and then augment one more column, which is formed by multiplying phi with gamma. In our case, gamma was 0, 3. That's the first column. And now we need to multiply phi with gamma. And the structure of gamma says, oh, take the first column and scale it by 0 and add that to 3 times the second column. That's what multiplying or post-multiplying phi with gamma is doing. And 3 times the second column of phi says, oh, take 3 times 1, 0. So that's now phi gamma. And if we find the determinant of that, we have the product of the diagonals minus the product of the off diagonals minus 9. Is our system controllable? We just needed this to be non-zero, not non-negative. We just need it to be something other than 0. This is not equal to 0. So, in fact, that choice of 0.8 plus and minus j 0.2 for closed loop poles could have been anywhere we wanted in the unit circle. And we could have found values for K1 and K2 to make that happen. That's what this controllability check allows us to conclude, which is why typically this is what we do first. We immediately check, is our system controllable? So now if we can locate our closed loop poles anywhere, that seems to be counter to what we were doing with the root locus or the transfer function based controller design. Where could we locate our closed loop poles when we were doing root locus based design? Where were our closed loop poles? Only on those red branches of our root locus. Was that the entire z-plane or was that the entire unit circle? Was it easy to locate closed loop poles inside the unit circle with the transfer function based design? Depending on your definition of easy, right? Or how you might want to. So are we getting away with something? Did we put our hand in the cookie jar and actually sneak out some cookies without anyone knowing? That sounds kind of nice, actually. But are we getting away with something? What's going on now that we are doing full state feedback in contrast to the transfer function based approach that was using the root locus as our design instrument? Hopefully you have your eyes closed as I scroll back, or you've taken your Dramamine, or you have your head down. And that's acceptable. You guys have been working hard and successfully completed your mission. So, what are we doing here that's different than what we did before? What's going on in this block diagram that might be different than what we were doing before in the transfer function-based design? We are sneaking in to this system. This is our hand in the cookie jar. Our hand is going in and grabbing every one of the state variables. Before, what did we grab? We just had one maybe output signal to use, and we were feeding that back. Now what are we doing? We're assuming that we can go in ahead of the output matrix and access all of the state variables. The position, the velocity, the voltage, the current, the temperature, the pressure, and collecting those values at each time step as L is marching along. L is just advancing from 1 to 2 to 3. Every one of those steps, we pull off the state, scale it with K, and use that to drive or change the input to our system. So what we're getting away with now is we're assuming we can do a lot more than what we were assuming in the previous designs. Now we're saying we can go into our system and access all of the state variables. That's what we're getting away with. Our hand is in the cookie jar, actually. So full state feedback requires access to each component of the state vector. Are there any other concerns? So we're assuming this. This is a big assumption. What else do we have? And now let's go ahead and remind ourselves. I'm not going to scroll back this time. Let's just redraw our system. Here's our bank of delays. We have Nevada of those, and here is our state vector coming out. That now gets combined through the output measurement matrix to give us our output Y. Creating the state one time step into the future is now made possible by, that sounded like a commercial. This is made possible by, never mind, this open loop system matrix phi. That allows us to create sum of X, one time step into the future. We also have our input matrix that is directing how the input is coming into that next state vector at time step L plus 1. And what makes that up? Well, out here, we now also are measuring our state and using that to inform what we're doing at the input to the system. What do we know is possible? If the system is controllable, then we can pick K to move the dynamics wherever we want. K can adjust the dynamics arbitrarily. But, as Brody pointed out before, we're sort of just stuck with me kicking this system, right? Or it reacting to a disturbance or an offsets, initial conditions. We are not, right now, the way we've built it, able to inject a reference input to try to track. What we want to do is allow for that possibility. And the way that we will do that is we will go ahead and widen our paper and put something into that summing junction in addition to minus k x of L. What we want to do now is say, suppose that I not only have U made up of full state feedback, but also let's scale or inject a reference signal R of L and weight that by n sub 1. So if we have one input, if U is one particular signal, U of L, that's a scalar, and we have one input, reference input, R of L, then what's this capital N sub 1's size dimensionally? What's the dimension of N sub 1? It has to be multiplied by a scalar and produce a scalar. So N sub 1 is 1 by 1, it's a scalar. Even though it looks like a matrix because it's capitalized. But N sub 1 is a 1 by 1 scalar. What we want to do now is realize that there was no way in the earlier full state feedback strategy that we were talking about to put in a tracking signal or a reference input, no way to provide a command signal, which is the little r of L, to the system. And that is what we were calling this regulator system. That was without the capital N sub 1 times R of L. In the regulator system, we had a system that, if it was kicked, would shake the way we wanted it to shake. The system has desired dynamic response. To initial conditions, and what we just wrote down in red, well, in this part, is now we have introduced a reference input. So the question was, can we introduce a reference input and that was a rhetorical question. Yes, since we've already done it several comments before. So now let's look at doing that and see what we can accomplish with introducing that reference input. And it's going to be used for tracking. We are now going to bump up our strategies in state space controller design to move a little bit beyond just having full state feedback and introduce a reference input so we can have tracking available. This is now reference input with state feedback. Or another way of thinking of this is we could say tracking a reference input R of L. So if we had R of L at 2, we want to, in the steady state, be able to lock on to 2. Then if we adjust that to 5, we can lock on to 5. And how will it go from 2 to 5? Well, it will have the dynamic behavior that we established with that full state feedback gain matrix. It will move the same way it moves with respect to these initial condition responses. Just to keep things a little bit less complicated, let's go ahead and assume that we're dealing with a scalar input. Or only one input. So that now our input to the system, U of L, is what we just learned. We're not throwing that out. We're keeping that. We liked that. We like to be able to adjust our dynamics arbitrarily. Our system is controllable. Now we can find the K that we want. But let's also introduce the ability to track a reference input R of L through this additional piece making up the input U of L to our system. If you wanted to think about this, if we have a scalar input, you could think of U of L being some 1-by-1 quantity. And if we had 4 state variables, then K would have 4 adjustable variables, K1, K2, K3, K4. X would be a 4 vector. A 1-by-4 times a 4-by-1 gives us a scalar. That's right. And now we want R of L to be a scalar. And we want the product of N1 times R to be a scalar. So we now need N sub 1 to be a scalar. And the product of those will now, on the left, give us a 1-by-1. On the right, those two products added together will give us a scalar also. Let's now work through these equations algebraically, or with the matrix notation. Our system hasn't changed. It's still a state space representation. It's X of L plus 1 is phi X of L plus gamma U of L. What we have changed now is we've kept full state, but we also have the reference input. Or now our input to the system, little u of L, is now minus K X of L. That's the full state feedback, plus N sub 1 R of L. Let's now see what happens when we use this structure for the input U in our system equation. Let's replace that and try to follow that all through and see if we can find a way of determining a transfer function between the reference input R and maybe our output Y. And if we want things to be tracking nicely, then maybe we want that transfer function to have a DC gain of, and not 3, huh? We want a DC gain of 0 dB or 1, right? In absolute sense. So we want the transfer function between R And what we haven't shown here, our output y, if it's a 1 by 1, one input, one output, we want that DC gain to be unity. Let's see if we can find what that means as far as how we would select this matrix n sub 1, or this scalar, this 1 by 1 matrix n sub 1, which is a scalar. We have x of L plus 1 is phi x of L plus gamma times this new structure for u, which is minus k x of L plus n sub 1 r of L. Nothing exciting there. We're just replacing u of L with what we defined it to equal. Full state feedback with a reference input. This is now our u of L. But we can start collecting terms that are scaled by similar matrices. We have x of L in a couple different places. We have phi minus gamma k. Both of those are scaled or post-multiplied by our state vector x. And this term or matrix we've called phi sub c. And we know how to design phi sub c. We know how to pick k by selecting our desired characteristic polynomial. We also have a piece that's associated with our reference input, and that's now plus gamma n sub 1 r of L. And we haven't changed anything with respect to our output. Our output y is still h times x of L. That's our output relationship. What do we want? We want to have y, the output, tracking r, which means we would like to be able to select n sub 1, which is a scalar if it's a 1 by 1, if it's a single input, single output system. N sub 1 will be a scalar. We want to figure out how do we find what we want n sub 1 to equal. And what we just said is let's find the transfer function between little r and the output and set that transfer function to have a DC gain of 1. So we're going to find this transfer function as a function of z. And what value of z do we use if we want to look at it at DC? Again, 1. At z equal to 1, right there on the z-plane. So let's now find our transfer function. From the z-transform of our reference input, which is capital R of z, to the z-transform of our output. Maybe what I should do is just z-transform that output equation first and keep that in our hip pocket, just like we want to put that check in our hip pocket that's posted up against the front wall. Congratulations to team 16080 for getting a $500 check today. All right, where was I? Oh, I was z-transforming before I got starry-eyed with that check. We now have y of z is equal to h x of z, and we need to applaud that team for even showing up to today's class, right? That's now y of z is equal to h x of z. That's z transforming because that's just a linear relationship. H is a constant, so we can easily z transform that. We want to now z transform this dynamic equation. And we're trying to find the transfer function, so we don't care about initial conditions. We can neglect those. So what happens when I z-transform little x of L plus 1? What happens when I z-transform an advanced time domain vector? We operate on it by z, don't we? So now we have z-transforming the dynamics. We have z times capital X of z. Again, we're neglecting initial conditions because we're worried about a transfer function. That's equal to, now I'll simplify that and say just worry about the closed loop system matrix, phi sub c times X of z plus gamma n sub 1 r of z. And we want to be able to factor out the capital X of z from all of these terms so we can introduce an identity matrix between this scalar z and capital X of z. We haven't changed that at all if we put inside there an n by n identity matrix. And that now allows us to factor things out. Now we can combine these two terms. We have zi minus capital phi sub c times capital X of z, and that's now equal to gamma n sub 1 r of z. Or if we pre-multiply both sides of this equation by the inverse of zi minus phi sub c, we can actually solve for capital X of z. That's now zi minus phi sub c inverse gamma n sub 1 r of z. And we want to now use that X of z in that output equation. Or capital Y of z is h times X of z. Well, X of z is zi minus phi sub c inverse gamma n sub 1 r of z. This is now our closed loop transfer function between the reference signal r and the output y. And what we want to do now is select this scalar n sub 1 for the transfer function t sub c of z to have a DC gain of 1. Or, stated another way, we want t sub c of z at z equal to 1 to equal 1. Or if we replace this scalar z with 1, we'll just have the identity matrix, and we'll subtract from that identity matrix the closed loop system matrix, phi sub c, form that inverse, and now pre and post multiply that by h and gamma. N1 is the only unknown we have in this equation. We're trying to solve for that. Forcing the DC gain to equal 1 says that we now have h times z, but z is 1 for DC. We have I minus phi sub c inverse gamma n sub 1 is equal to 1, where we have assumed, or we've already put in, z equal to 1 for our DC value. And if we have SISO, since many of you are texting, this is single input, single output. That's what that stands for. So gamma is one column wide, h is one row tall. So h I minus phi sub c inverse gamma is just a scalar. We can divide by that and solve for n sub 1. This now says that h I minus phi sub c inverse gamma is a scalar. And if that's the case, now we can say n sub 1. In this expression, we have a scalar times a scalar equaling 1. Just divide both sides by that one scalar to solve for the unknown n sub 1. Or n sub 1 is now 1 over h I minus phi sub c inverse gamma, where this is a scalar. And that's how we would pick n sub 1, to have good tracking. And we'll pick up at that point, and I'll give you an example lecture illustrating this on a particular system, the mass spring damper, and that will be lecture 8.3 when this is lecture 8.2. And we'll pick up for our final lecture on Wednesday.